Today I wanted to start talking about big O notation. Big O notation is used when you want to measure how fast a program runs in terms of the length of its input. So, in computer science, we're concerned with writing computer programs, and these take inputs, and they produce some sort of output. And what you're really concerned with, well, one of the things that you're most concerned with, is how fast does this particular program run? How do we measure that? How do we understand that? One way would be to take a bunch of different inputs, input 1, input 2, input 3, feed them into the program, and just see how long it takes the program to run in, say, seconds. So maybe this takes 100 microseconds, maybe this takes 2 minutes, maybe this takes 3 seconds. We just have a whole bunch of different inputs and a bunch of different outputs. But somehow this isn't very scientific or principled or mathematical. And so the standard way that a computer scientist understands how fast a program runs is in terms of asymptotic notation or asymptotic analysis. And all this really means is you let n be the length of the input and express the running time as a function of n. So, for example, if we have this program here, we might be interested in, trying to prove that on inputs of length n, maybe this particular program, this is just an example, maybe this particular program runs in time 2 to the n. So it takes 2 to the n steps to execute. Now, if we know this particular fact, that on inputs of length n, it takes at most 2 to the n steps to execute, okay, well then, if I have an input of length 10, then I know no matter what this input is, as long as its length is 10, that the program is going to take, at most, 2 to the 10 steps to run. And if my input is of length 100, then, my program is going to take at most 2 to the 100 steps to run. Now, one thing you'll notice is that 2 to the, well, you may not know this, but 2 to the 100 is an absolutely enormous number. It's more than the number of elementary particles in the universe. So if your program takes 2 to the n steps, and n is 100, and your computer program takes 2 to the 100 steps, it's never going to halt, even if it's the most advanced computer system out there. Now there is this issue, what is a step? Right? Depending on, say, the programming language, so a step may vary from programming language to programming language, or from architecture, computer architecture 1, to computer architecture 2. Depending on what programming language you're using or what architecture you're using, an addition may take more time to carry out on architecture 1 than in architecture 2. It might take more time in programming language 1 and programming language 2. And we sort of don't really want to worry too much about when you're analyzing the running time of a program, it's annoying if we have to constantly worry about what programming language we're using and what computer architecture we're using. So we're a little sloppy when we measure the running time of an algorithm. And that's what sort of big O notation is. So, for example, if with respect to programming language 1, the algorithm runs in time let's say the algorithm runs in time 3 times 2 to the n. And on programming language 2, the algorithm runs in time 3.5 times 2 to the n. Well, what I'm really interested in is that there's a 2 to the n sitting here. I'm sort of less concerned about the constant 3 versus 3.5. What's really going to tell me how quickly this program is going to run is this term, 2 to the n, 2 to the n. It's going to really sort of dominate the running time. It means that, the algorithm is going to run slow, sort of regardless of the programming language. What big O notation basically does is it says, ignore constants. We don't really care if there's a 4 here or a 10 here. What we really care is that there's a 2 to the n and a 2 to the n sitting here. So we say f of n is big O of g of n. So f and g are both functions. We say f of n is big O of g of n if there exists a constant c and constant k such that for all n greater than k, the absolute value of f of n is less than or equal to c times the absolute value of g of n. Don't let the absolute value symbols worry you so much. For this class, we'll just always assume when we're using big O notation that, we'll usually assume that f and g are positive functions, and so taking the absolute value won't do anything. But what f of n is big O of g of n really means is that as n gets really large, f of n is always some constant less than or equal to some constant times g of n. So maybe I should write that in quotes. Let's say for n sufficiently large, f of n is less than or equal to some constant times g of n. This is sort of an English translation of when I write f of n is big O of g of n. Okay, so for example, let's let f of n be 4n. Okay, now it is the case that f of n is big O of n. Why is that? Well, we need to prove, or need to show, that for sufficiently large n, f of n is always less than or equal to some constant times n. Okay, so more precisely, we need to show that there exists a constant c and k such that for all n greater than k, f of n is less than or equal to some constant times n. This is what we need to prove to show that f of n is big O of n. So we need to show that there is a constant c, there are constants c and k, such that for all n greater than k, f of n is less than or equal to c times n. So I'm going to pick my constant c here to be 4, and we'll pick just k, we'll set c to 4, and we'll pick k to be 1, let's say. And then what I'm claiming is that for all n greater than 1, f of n, which is 4n, is less than or equal to c, which is 4, times n. And this is obviously true for all n greater than 1. 4n is less than or equal to 4n. I mean, 4n equals 4n, so it's less than or equal to 4n. But what we've shown is that there exists a constant c, namely 4, and k, namely 1, such that for all n greater than k, f of n is less than or equal to some constant times n. So for all n greater than 1, f of n, which is 4n, is less than 4 times n. This implies that f of n is big O of n.